Hello students, today we will discuss on electric field intensity due to uniformly charged thin spherical shell. As you see the diagram, it is charged with positive polarity and the radius of this shell and the radius of this shell is considered as capital R. What we are going to do now, we are going to find out the electric field intensity at a point which is outside of this shell, which will be on the, or a point which is on the surface, or a point which is going to be considered inside the shell. So what we are going to do, we are first going to draw Gaussian surface. Everywhere we are going to draw Gaussian surface. It will make our life easier to find out the electric field intensity. So let us do a Gaussian surface. Let us do a Gaussian surface that is outside of the shell. Here one point I should tell you, you can also consider any point anywhere outside the shell, and from that point also you can draw the Gaussian surface. It's of your own, it's your choice. So let me take a point P over here which is on the Gaussian surface and also outside the actual surface of the shell. Let us consider another Gaussian surface that is inside the shell. Here also I am telling you, you can also take any point. Let me take P dash over here. You can take any point and then also you can draw the Gaussian surface. Your wish, which one you do earlier. And let us consider the distance from here as say small r, the small r till that distance. Now what we will be doing, the same thing what we used to do. At this point we need to take the electric field. Obviously we need to consider a small area element always radially outwards. I have told earlier also, radially outwards means it will be outward and also perpendicular to the surface. So dA is perpendicular to the Gaussian surface and also outward. As soon as we take a point, that means we are bringing a test charge over there. Since it is not mentioned, that means it is always you need to consider as positive. The source charge here is the shell. So shell is positively charged and you are bringing a test charge which is also positive. So that means it will experience the force in this direction, repulsion force, and the force and the direction of the force is also the direction of the electric field that we have already discussed earlier. So this is your E now. So this is your E which is parallel to dA. Both are vector quantities. I have put the vector signs also over there. So now if I find out over there, let me make it the center as O. So for the small area element, let us have a small flux coming out from that, d phi E. So d phi E is E dot dA, the same things whatever you have done for earlier cases also, for line charge, for parallel sheets, all those the same concept. Every time we are using the same one only, E dA cos theta. Theta here is 0. Theta here is 0, and since it's a spherical one, so each and every portion you will always find these two are parallel to each other. Theta is 0, so you are landing to d phi E as E dA. Now if I want to find out the whole of the flux, then simple, phi E equal to integration of d phi E, that is the total flux. So this is E dA. Hope you understand. E is constant. Why E is constant? Because radius r is constant, this r, the distance is constant, and also the charge is constant. So obviously the electric field will be constant. So it is coming out, and sorry, we need to consider dA. Then inside that is only the variable over here. So E dA, if I integrate this one, the total area, we get A, that's the area of the surface area of the sphere, over here. Then surface area of sphere is 4 pi r square. R square is the distance, r is the distance, so r square. Now by Gauss theorem, what we know? By Gauss theorem we know that phi E, that is the total flux, is 1 by epsilon naught times of the charge enclosed, and let us consider the charge enclosed within the Gaussian surface. I am not writing over there, take it as Q. Then let me write this as Q by epsilon naught. This is your equation 1, this is your equation 2. So what you get over here, if I compare these two, I will be getting E 4 pi r square equal to Q by epsilon naught. This one I can again write as E 1 by 4 pi epsilon naught Q by r square. So what we conclude over here, that the expression of electric field for a point charge is same as that of a spherical shell. That means whatever the distance may be, that r or the point P, this shell will act as a point source charge. Hope you understood from this expression. Now you got this one. If you now consider, say let us consider this one as surface charge density, as say sigma as the surface charge density. That means this much of coulomb per meter square. If I consider this one, this much of the coulomb per meter square, then Q will be how much? Sigma into A, total surface area. Sigma is the surface charge density, that means this much coulomb per meter square. Let me put in over here. So this is sigma, total surface area is 4 pi r square. Now this r is not this r. So what you need to do, this r is what? This is the radius of the sphere. See, Q is the charge on the shell itself. That means whenever I write 4 pi r square, this r is not the distance but the radius. So that means you need to put this one as capital R square. Hope you understood. I am telling it again, when we are writing for this one, when we have done this part, we have taken 4 pi r square. This r was the radius of the Gaussian surface. Now whenever I am writing this one as r square, then this r is nothing but your radius of the actual sphere. So you got 4 pi r square. Now electric field then stands as E equal to 1 by 4 pi epsilon naught into Q. This Q is substituted by the value of 4 pi capital R square by small r square. So you get 4 pi will get cancelled out. So E stands for 4 pi cancels out. E stands for sigma by epsilon naught into capital R square by small r square. So this is the other expression. So sigma by epsilon naught, capital R square by small r square. So there are two expressions for this shell. One is this one, the second one is this one. Only thing we have considered the sigma as a surface charge density. Now this expression stands when r is more than the radius. When r is more than the radius, that means outside. Now if I consider the other two conditions, when r is less than, or let me make it first equal to r, that means P is on the surface. P is on the surface. When P is on the surface, that time what will happen? Simple, we'll put this one only, expression E equal to sigma by epsilon naught r square. This small r is equal to capital R, that means r square. So you get sigma by epsilon naught. That is when r is equal to capital R. Now if r is less than capital R, r is less than capital R. Now in this case you need to understand, for a shell, the surface, the charge resides always on the surface of a shell. That means inside part there is no charge. So if I go to consider this electric field also, this is of no use. The reason is because charge resides outside or on the surface. That means no charge in the, or you can write inside the shell. So there are three conditions what you found out. First is when the point object is when the test charge is brought outside of the shell, you get these two expressions. From these two expressions we have come to this point. From here, when the point P lies on the surface, that means small r will become equal to r, that means this small r will shrink and it will come over here, that means equal to capital R. So you will be getting this expression. And when small r goes near less than capital R, that means it is inside. So inside there is no charge, the charge resides always outside of a shell. So then if charge is not there, how come the electric field will be there? So hope you understood this part. We will go for the next part where we will discuss, that will be the last part almost, where we will be discussing on uniformly charged. Instead of theory in spherical shell, we will be discussing on sphere. Thank you, hope you have understood. If anywhere any confusion, please let me know, and I'll try my level best to give you more concepts on the basis. Also numericals will come out from these parts also. So these are only the theory, these are only the derivations from here, or the concept building parts, from where we will shift to the numerical part also. Thank you.